All right, so we'll get started. Everyone can hear me fine? Yeah? Cool. So, of course, it's the second last talk of day 2, so we'll try and keep it interesting. And in fact, what we're trying to talk about here is compression in general, how it works in Hadoop. And then we'll talk about some specific work we have done in this area. So let me first introduce ourselves. Govind is a software developer in the Hadoop services team. He focuses a lot on HBase and Hadoop performance, and he's got a very good systems background, primarily in the performance area. My name is Sumeet Singh, and I lead the product management team for the Hadoop at Yahoo. And before that, I also focused on strategy functions for the cloud platform group. So let's get started. We have tried to address all types of audience. If you're new to Hadoop or you've just started using Hadoop, I think you'll find the first 3 agenda topics useful, which is a general introduction to how compression works in Hadoop, what are your options that you have available in Hadoop, and then finally, understanding those options in a bit of detail and then working with them in Hadoop. And then the second half of the talk is mostly about the problem we faced at Yahoo that where actually compression helped. We'll talk some of the performance evaluation runs we conducted to solve that problem. We'll talk a little bit about native bzip2. So if you have worked with Hadoop, you know that bzip2 is only in Java version, not in native version. So we'll talk about that. Then we'll also talk about the performance results by using IPP libraries and whether it helps or not. And then finally, we'll wrap up. We'll talk a bit about the future work that is possible in this area. And then we'll open it up for Q&A, right? So some specific work in the last section, a lot of general introduction in the first section. Okay, so why is compression important in Hadoop? Hadoop is designed to operate on very large sets of data, right? So compression naturally helps. But even though it's intuitive that it will help in general, I think it's important to understand the trade-offs that you make just by using compression in Hadoop. And there are some very significant trade-offs. And then we'll talk about the trade-offs that you make when you choose your options. So Hadoop jobs are data intensive, right? And what that means is that you have a lot of I/O operations. MapReduce jobs are almost always, I won't say always, almost always I/O bound. They're not CPU bound. So if you compress your data, you can speed up the I/O operations. So that's the first benefit of compression. The other benefit is that storage space is always at premium, particularly when you're working with very large data sets. Right? So if you compress your data in HDFS, you can save storage space. In fact, Hadoop also has this thing called 3x replication by default that's built in the framework for fault tolerance. So if you compress your data, it involves a lot of network transfers among data nodes. So you could, again, save or speed up these network transfers if you're compressing data. So that's yet another benefit. So your resource utilization for the cluster and your just cluster, what it can do, can go further, the current hardware. And finally, if you have these benefits, which is reduced I/O and then speed up of network transfer, what you would experience in general is that your job performance will go up, which means that your MapReduce jobs can finish faster. Okay, so lots of benefits, but it doesn't come for free, right? You expend a lot of CPU cycles in compressing and decompressing data. So quite basic. But it's still important to understand the trade-off. On one side, you've got these benefits, which is storage, disk I/O improvements, network bandwidth savings. And then on the other side, you're trading all of this with CPU time in compressing and decompressing data. Okay, so let's look at how compression interacts with MapReduce process in detail. So what this is essentially the 3 phases of a MapReduce pipeline. The purple box here is where I would track compression as it happens in the pipeline. And the blue box is where I'll track data decompression, because data has to be decompressed if further processing is needed in this pipeline. So in the very first phase, you could bring in your data compressed, in which case, based on the file extension, typically, map task will automatically understand that it's compressed. And if it has support for that codec, it will decompress that data for further processing, right? Again, And then once the map outputs the data, it gets into this phase we call a sort and shuffle. And that's important to understand because what happens is the map outputs is getting buffered in memory, and then memory can only hold so much. So there are spills to the disk, in effect, in this phase. Right? So there are lots of spills file created, they're merged on the disk, and anytime you're writing to the disk, you're generally going to benefit from compression. And this is an intermediate phase as well. This is not your final phase. So this is not the data that has to live forever. So that's another thing that's important to understand. So your map output can be written compressed to the disk, particularly in case where there's spillage. And then the reduce phase, which is the final phase in this pipeline, can take that data compressed if it's compressed, and it will decompress that for further processing. Okay, and multiple, given that the map outputs can live in other data nodes, which this reducer needs, there is a network transfer involved. So if you're writing compressed on the disk and you're bringing it uncompressed, you're benefiting by network speedups. Okay, and finally, when you're writing your reduce output to HDFS, you can benefit again from compression, right? So that's the third phase, so you can write the output compressed. And generally, you will see a better write throughput. Okay, so that's how compression works in sort of a MapReduce pipeline. It's pretty integral to the pipeline itself. So it's important to understand the options that Hadoop supports for compression. And given how important it is, Hadoop's got a plethora of options, like lots of options. There are 6 in particular. And what it's important to understand is that each of these formats that you use for compression in Hadoop is based off of some basic algorithm. Most often than not, it's the Lempel-Ziv 77. It was done in 1977. That's where 77 comes from. Based off of that, or some variant of that, or Huffman coding, or a combination of these, except gzip2, which actually works on a transformed-based algorithm, which in this case is Burrows-Wheeler transform. So I'll talk a little bit about what the strategy means when it comes to these specific algorithms, right? So there are 2 broad strategies. One, as I was describing, the transform-based strategy, where you actually take the text string and sort of permute that string in terms of trying to find space savings or redundancies, right? Any compression actually has 3 phases. The first phase is about detecting or pre-processing or transforming. The second phase is about finding the duplicates. And the third phase is about bit reduction. And almost all of these algorithms, how it works in these 3 phases, has a deep impact on what it does. Several of these, the first 2, are dictionary-based. And what that means is that you keep a dictionary of strings, and you replace the string where you find that in your data with some marker. So essentially, you're trying to remove redundancy in data, and that's how you achieve compression. These are all lossless, so you have to recreate the data back as it was when you're decompressing. And transform-based, I already talked about. And then there are 2 other sort of general strategies involved. One is called bitstream, and the other one is block-based. So, for example, gzip zlib works on a stream of bits, right? So you're compressing the stream as they're coming in, taking the stream out. On the other hand, bzip2 sort of works on a block of data. So you're compressing a big chunk, then again compressing a big chunk, then again compressing a big chunk. And then each of these codecs has a particular emphasis. It's either trying to save you storage space, or it's trying to speed up the process, or the compression process or performance of the codec. zlib is the default codec, deflate, that's used in Hadoop. gzip is a standard, or bzip2 as well, is a standard utility. The other 3 are sort of the newer codecs, and they are, I would say, optimized for speed. So you would see specific applications of those in a MapReduce pipeline, or in a MapReduce job, or pig job, or other things. So we'll talk about that. Right, that's a general introduction to the algorithms and codecs at a very high level again. So when it comes to Hadoop, all of these codecs are defined in what I'll call as iocompression.codec. And then each of these Java classes, you can see the definitions, and you can recognize them, what codec has been operated on the data if it's compressed by the file extension. Pretty straightforward. If you read the extension, you can figure out which one was used. The other important aspect to understand is splittability of data and these algorithms. And the only splittable algorithm in real sense is gzip. The other ones can be made splittable too because they're block-based, like LGO, LG4, or Snappy. And what splittability means is that you can use the parallel nature of MapReduce jobs while decompressing. Otherwise, you have to use a single task to bring all the blocks together and then decompress. So splittability is important for speed up as well. And then Java versus native, almost all of these have a native implementation. And some of the top 3, the older ones, have Java implementation. In fact, gzip 2 didn't have a native implementation. So if you read like the Tom White's book, the Hadoop Definitive Guide, it shows us N. It's a yes now, and that's the word Govin's going to talk about. So I talked about splittability. I highlighted that. LZO is also a bit of, I would say, something that I need to highlight because there were licensing issues for which it was removed from Hadoop, but Hadoop still supports it, so you can download and use it. And then finally, I did talk about the native and versus Java of these codec versions. So since it's a tale of trade-offs, now you've sort of seen that compression itself presents trade-offs. The options that you have for compression also presents trade-offs, right? And this trade-off is typically in terms of space and time. And as I was saying, based on the emphasis of what these compression algorithms focus on, some focus on space saving, some focus on time, you can see that actually gzip2 and zlib or gzip actually do pretty well on space savings, but not as much on time. So the y-axis is the compression, decompression time combined. And the faster codecs, Snappy, LZ4, and LZO, actually do very fast compression, decompression, but don't save you as much space. So it's important to understand that. So if you had an ideal codec, it would show up on the extreme right bottom, right? No time taken, a lot of space savings. So those are kind of creates 2 categories of codecs. One on high compression ratio, one on high compression speed. Okay, and Hadoop job conf parameter has the settings that you can work with when you're working with these codecs. As I said, in the input data, map recognizes the extension and decompresses the data for processing. For sequence file, this information is contained in the header. So sequence file is something that sort of forces splittability. And then intermediate one, you can turn it on and off. You can choose the codec. And then the final phase is, again, you can turn it on and off, choose a codec. And for sequence file, you can choose to operate on record level or block level. So the settings in the job conf parameter are pretty straightforward. So how should you think about then using these codecs? So in the first phase, which is the map phase, you want to compress your data if the data is large. So if it's in gigabyte order, let's say, you want to compress it. And then at that time, you want to use something which is splittable, like gzip2, or you should force splittability with sequence file and use zlib, right? In the intermediate output, since it's a transient data, you always want to use compression. You will always benefit for compression. And the other factor here is the shuffle and short phase is sort of moves data in between network. So it's particularly true if you have disk spillage or slow network transfers. You definitely want to use compression. And then you want to use something which is very fast, like the faster class of algorithms, LZO, LZ4, or Snappy. And then in the final phase, if you are writing the data into HDFS for storage or archival, or if you are wanting better write throughput, or if it's a chained MR job, what it means is that one MR feeds to another MR, you want to compress that. And then in the cases where you want to work on and off the clusters, you want to use a standard utility so that people off of Hadoop can understand your compressed data. And for intermediate data exchanges as well, you want to use something that's understandable. Okay, moving on. So Hadoop itself gives you a lot of options. And the tools in the Hadoop ecosystem, things like Pig, Hive, and HBase, also provides additional support on top of what Hadoop does, right? So, and then they all default to Hadoop configurations. So if it's a Pig job where you're executing multiple MapReduce jobs, we talked about this chained MR job, so that intermediate phase where you're making data go from one reduce phase to the next map phase, you want to turn pig.temp compression to true. Okay, and then you can choose the codec. It has choices for gzip and LZO. We typically use LZO. I'll show you some results because that's the intermediate phase you want to be fast. Hive also has support similar to what pig does. So if it's an intermediate phase, which is between these MapReduce jobs, you want to turn compression intermediate to true. Or if you're writing the final output back into Hive tables, you want to set the compressed output to true. And then everything else, as I said, defaults to what MapReduce job count provides you. HBase as well provides support for compression at the column family level. So you could specify the compression parameter while you're creating the tables or after you've created the tables. All you need to do is disable the table and alter the table with the compression parameter. Right? So Hadoop and the Hadoop ecosystem components both provide very good support for compression. And you have the choices of these codecs as long as you understand what you're trying to accomplish. So, you know, Hadoop at Yahoo is pretty large. So let's see what we have been doing. So I looked at the input data to the map phase. So I looked at about 380 million files for a day in the /data/project directory for some of our production clusters. And I see that 98% of the data was compressed. A lot of these were sequence files, actually. But if you look at what I had described as gzip being the standard utility, some of those are coming in standard from off-grid locations. Intermediate phase, almost 100% turned compression on. And they're using LZO, which is the faster version of a codec. And then in the final phase, which is the reduce phase, it's basically, again, for LZO, we also take a lot of data uncompressed for downstream analytics. But gzip is also prevalent, and LZO is prevalent for transfers between MapReduce jobs, so chain jobs. So with that, I'm going to turn it over to Govind to talk more about the problem he was trying to solve with compression and his work.
Sound check. Sumeet has just given an excellent exposition on the various aspects of data compression in Hadoop. Now, I'm going to talk about a compression issue we faced on our clusters having to do with data storage efficiency. As you're probably aware, Yahoo operates some of the largest Hadoop clusters around. We move petabytes of data around every day. A year ago, we noticed that we were running out of storage capacity on some of our clusters. We tried to address that by switching from the sequence file to the RC file format. In the RC file format, column data is stored contiguously, and that gives compression algorithms a chance to compress more effectively. In fact, we were able to see about a 25% improvement in compression by making just that one change. Another strategy we considered was to use bzip2 for compression. For our data sets, we were able to get about a 15 to 20% further improvement by using bzip2. But the downside of doing that was the increased computation effort and the potentially longer job times. We considered alleviating that by using a faster implementation of the bzip2 library, in particular, the IPP library. I will talk about IPP in the next slide. However, there was a fly in the ointment because, as Sumeet said, the bzip2 codec is the one anomalous codec that does not have a native code implementation. So in order to have it load native code, we needed to rewrite it. That work was done in collaboration with Jason Lowe, Hadoop Core PMC committer, and checked in as Jira 8462. This is available in the latest versions of Hadoop, 0.23.7 and above. So once we had this native code codec, The next step was to use it to substitute the IPP library for the standard system native code library. Now, I'll say a few words about IPP. It stands for the Integrated Performance Primitives from Intel. This is a set of highly optimized libraries in a variety of domains, such as string processing, image processing, cryptography, lossless compression, and so on. How does IPP achieve its speed up? For one thing, the algorithms have all been rewritten to work better on modern multi-core systems. And the other technique is architectural improvements. As you know, processor technology has evolved considerably in the last decade, and processor vendors have been busy adding new instructions to the instruction set. In particular, now we have the SIMD instructions, vector type instructions, single instruction, multiple data, where one instruction operates on multiple words, data words at a time. Compilers find it difficult to generate code that takes advantage of these instructions. So one way to do that would be to use libraries such as these. The IPP library detects the model of the processor the code is running on at runtime, and then it loads precisely that subset of primitives that is targeted for that model of the processor. In the case of compression, there are primitives available for lempel-ziv, for Burrows-Wheeler transform, run-length encoding, LZO, and so on. Typically, you would not use these primitives directly, so IPP offers drop-in replacements for high-level formats, such as zlib, gzip, bzip2, and LZO. To measure standalone performance, we use the standard utilities, such as bzip2 and gzip2, off the shelf, where they were available. But in the other cases, like for Snappy and for zlib, we wrote driver programs to actually exercise them. The runs were all carried out in 32-bit mode because our Hadoop data nodes are running in 32-bit, and they were run in single-threaded. In the case of the Java version, we explicitly discounted the overhead of loading the JVM. Every compression format has a parameter that allows you to specify the computation effort that you want to expend. And in all these cases, we just selected the default level. We didn't change that. The runs were all carried out in quad-core Xeon machines. Compression is highly dependent on the nature of the data that's being compressed. So it's essential to use a wide variety of data sets. In our case, we used binary files, text files. We used a 265 megabyte corpus from Wikipedia, and finally the Silesia corpus. This is a collection of data sets in a variety of areas, such as program files, binary files, image files, foreign language files, and so on. So it's a good representative sample. In the past, we had the Calgary corpus and the Canterbury corpus that was used for measuring compression, but those typically had much smaller data files. Today, in this age of big data, the Silesia corpus is more representative. This chart shows compression ratio for the various different codecs. The different colored bars in the histogram represent the 4 different data corpuses that we used. On the y-axis is the file size in megabytes. So the shorter the bars, the better the compression. As you can see, and in lines with what Sumeet said, zlib and bzip2 really emphasize compression ratio, so they compress down to a much smaller size. And you can see that bzip2 does better than zlib over there. And on the right side, you have the fast compressors, LZO, Snappy, and LZ4, which are roughly about compressed to about the same compression ratio. The flip side of the coin is compression performance. On the y-axis over here is CPU time in seconds. And you can see that this slide is for the standard compressors, zlib and bzip2. The yellow bar in the middle is just taken as a sample. That's the performance with the Wikipedia corpus. And we can see in this particular case that the IPP version of the library does better than the standard open source version of zlib. You will also see that in the case of bzip2, IPP bzip2 has an even better performance than the open source version of bzip2. The other fact that stands out is that native code generated from C performs better, much better than the Java version. In this particular case, we see about a 40 to 45% improvement. Now, this is an apples-to-apples comparison of the performance of code running for bzip2 and for the Java bzip2. This slide is the equivalent slide for the fast algorithms. So here we have LZO, Snappy, and LZ4. The bars seem to be about the same height, but then the speed up is really an order of magnitude faster than the standard compressors. Over here, we can see that performance of LZ4 seems to be somewhat better than that of LZ4 and LZO and Snappy. The y-axis again shows CPU time. With regard to decompression performance, we see the same pattern once again. Here we have IPP zlib and IPP bzip2 performing better than their open source counterparts. We also see the improvement of the native code over Java, just like we saw on the compression. Again, decompression for all the formats is much faster than compression, but the trends are very similar. Finally, the slide for decompression for the fast algorithms. And again, we see the same kind of trends. LZ4 seems to have the edge over LZO and Snappy in this particular case. And this is all the 4 different data sets that we used. With regard to compression performance within Hadoop, we used the Daytona Performance Analysis Framework. This is a framework that we are in the process of open sourcing. And we used Gridmix to carry out our measurements. Within Gridmix, we used the load-gen and sort jobs. And our input data was sequence files compressed with zlib and with bzip2. For all our runs, we used LZO for compressing the transient data, the output from the maps. Our cluster was 35 data nodes. And in all these cases, we used dual quad-core Xeon machines. This chart shows map performance. On the y-axis is map time, the average map time for the tasks in seconds. And we see the performance for the different bzip2 codecs. zlib is just there for reference. So we can see that the map performance is pretty much the same, not very much different between Java bzip2, and IPP bzip2. zlib is better, but then the issue is the worst compression ratio with zlib. Now moving on to the reduce performance, this is the average reduce time. This time it's in minutes, so it's much more significant than the time that you see with the maps. For the maps, it was in seconds. And here we see that the bzip2 codec performs better than the Java bzip2 codec by about 10 to 15%. Now, that does not match the 40% improvement that we saw when we did the comparison in standalone mode. And that is pretty instructive because this drop is on account of the overhead of the JNI interface, the Java to native calls, which impose quite a bit of overhead. And there are associated buffer copies where data is transferred. So that eats into the performance improvement. But still, nevertheless, we see about a 10% improvement here. The other fact that springs out is the stellar improvement of IPP bzip2 over the other two, over open source bzip2 and Java bzip2. zlib is there for comparison again, and again, as I said, the compression ratio is different. Finally, this is the wall clock job end-to-end job time. The y-axis shows job time in minutes, and the slide is very similar to what we saw for the reduced performance. So that concludes the performance section. However, there's quite a bit of work that could be done in this area in the future. For one thing, the native code bzip2 codec does not feature splittability. This is not really a major downside in that it seamlessly falls back to the Java version of the codec when splittability is requested. But it would be a nice feature to add nevertheless. Pig currently has its own bzip2 codec for historical reasons. So it will not be able to take advantage of the improvements that we introduced with the native code gzip2 codec in Hadoop until PIG is enhanced to actually use the Hadoop codec. This is something that should be done in the future. As you saw earlier, the JNI interface imposes quite a bit of overhead, and the associated buffer copies are another issue. So revisiting that would be a fruitful endeavor in trying to improve performance. All our measurements were done in 32-bit mode, so when we move to 64-bit mode for our data nodes, as will be done in the future, at that point we might need to reevaluate some of these numbers. But this is current for the 32-bit case. I also mentioned that every compression format has an associated compression effort parameter, and that can be varied. It would be instructive to vary that parameter and see how these different formats perform against each other with different levels of compression. There are other areas that we could work on in the future, but I'm not going to cover that. As we saw, Hadoop offers a number of different options for compression. It's not always easy to decide how to select the right ones in your case. Sumeet gave quite a few guidelines on doing that. Many of them are in this slide as well. The first and foremost among them is that compression is very dependent on the type of data that's being compressed. So running the kind of standalone measurements that we did with our data, in your case with your data, would be very instructive. They would tell you what the right codecs are to choose for both the final compression and for the intermediate compression. Another factor to take into account is the frequency of compression versus decompression. Sometimes you end up having long-lived data that stays around for a long time and gets fed in as input to many jobs. In that case, you are compressing once but decompressing many times, and you might be willing to spend the extra effort to use a codec that gives you a better compression ratio. Data storage efficiency requirements, like in our case, might be something that can have an effect on the right codec that you want to use. If your clusters are running low on storage capacity, you might want to go with gzip2 or an equivalent codec that gives you better compression ratio. Or you can use zlib, perhaps with a higher level of compression effort. Sometimes there's a requirement for data to be taken off the grid, and you want data to be generated in some kind of standard format. So usually Snappy or LZ4 might not cut it in that case, and you would want to go with gzip or gzip2. Splittability is yet another requirement. The gzip2 codec is splittable. Otherwise, you have to use a sequence file to achieve splittability. I talked about 32-bit versus 64-bit options there. The size of the intermediate and final data, sometimes you end up ingesting a lot of data and producing much less. In that case, compression may not be as much of a consideration. Finally, alternative libraries like IPP might be something that you want to check out. What can you take away from this talk? We had a good overview on compression. We talked about a new native code codec. We looked into alternative libraries. And finally, checked out some performance measurements. They show that compression has a significant effect on Hadoop job performance. An easy way to improve the performance of your Hadoop jobs is to turn on the right types of compression for your data sets. Now I will call upon Sumeet to come up, and we will open it up for questions. There are 2 mics over here, so please use that if you have any questions.
Very informative presentation, thank you.
Oh, thank you.
Did you consider any hardware compression modules, even just to experiment the impact of them?
The question was about hardware compression?
Yeah, hardware offload, yeah.
No, we did not look at any hardware cards or any other. There are hardware devices that can give you compression, but with this library, we saw very good speed ups. So this was an easy way for us to achieve speed up rather than introducing new hardware to the clusters. Our clusters are very large in size, up to 4,000 data nodes and so on. So additional hardware would be a consideration to manage and decide how to take care of.
And
I also think that's a question of, how much effort you spend upgrading some of these nodes. Some of them are, and these things are all in different phases of their lives, and they're never uniform. Like a cluster has many different types of configurations, and then going to a data center, sort of upgrading them with some hardware-based plugin. I think we have to think about what cost do you actually save by, let's say, achieving 5% extra compression or savings versus the amount of effort you're going to expend inside operations, upgrading these nodes, and then the life of the node themselves. I would actually consider it if it turns out extremely positive that any of these hardware-based plugins or compressions actually saves us that much. But I'm a product manager, so I think dollars. I mean, it's just.
Another question. You presented the compression options in the context of MapReduce.
Yes.
Did you try anything, for HBase, like would something like similar would be applicable for other workloads?
Oh, I did talk about Pig, Hive, and HBase. Those are the options that are present in these components. And then when they actually, so for example, a Pig executes MapReduce jobs and Hive does the same. You actually default to what the Hadoop compression is when it comes to those MapReduce jobs. And then there are certain parameters that are on top of Hadoop for things, let's say, when a Pig script has multiple MapReduce phases. And when you are doing this intermediate sort of processing from one MapReduce phase to the next MapReduce phase, you're turning this temp compression on. Between the MapReduce pipeline, the phases, the 3 phases that I talked about, it's defaulting to the Hadoop compression mechanisms.
Thank you.
Hi, thanks for the presentation. I wanted to clarify one thing. Between the map and the reduce, I believe you said you should use the faster compression techniques such as LZO, and between in a multi-stage, you should basically use something like gzip between. Can you clarify that a little bit? Why is that so? Why not use LZO for both?
Yeah, you could if that helps your data in your case. But in the intermediate phase, in the temporary phase, the data is transient. So you're not necessarily storing it. You're not necessarily trying to save space. And given how heavy this phase is between map and reduce, because you're essentially trying to fetch multiple copies from different mappers, you go for speed. And when you do performance runs, there is no space saving there. So emphasizing compression ratio or space saving isn't important. It's a temporary phase.
But isn't everything transient in this case? So basically the way I read that slide was you have a Pig job which translates into multiple MapReduce jobs, and you're recommending use gzip in between. So isn't everything transient in that case?
Absolutely correct. So let's say you have a Pig script. Eventually, or not eventually, before the whole thing starts, it has to read data from somewhere for processing. That data doesn't necessarily have to be LZO compressed because it's stored somewhere in HDFS. You're thinking space savings at that time. Anywhere in between till you write the final output to HDFS, you're thinking speed. Like you want to go fast. So if you looked at our results on our clusters, all intermediate phases between MapReduce jobs is using LZO, right? And all the temp compression for Pig is using LZO.
So got it. I guess what you're saying is if it's on HDFS, then it's not transient anymore the way I was thinking of it. Even though it is intermediate data between the results.
I think it goes by what you need. Like if you need to save space, you have to go with zlib, gzip, or bzip2. If you want speed or quickness in compression or your job, where you don't expend too much CPU cycles doing compression, decompression, then you go with the speeder, the faster ones. But it won't save you as much space. So that's the trade-off. You have to understand what you're trying to accomplish.
Got it. Thank you.
You can take one quick question, I think.
We'll see if it's quick. I work for Lawrence Livermore National Lab, and we led the port of ZFS file system to Linux. So ZFS is a native file system, supports compression very well. So I wonder, I thought about the idea of if you just used the native file system compression, built HDFS on top of it, and let the file system handle the compression for you. It's much more coarse-grained, but it's also, you know, doesn't require anything of Hadoop. It's just done at the local file system level. Have you thought about that at all?
No, we didn't look at that, but that's something that could be done. I think we're running out of time. We could take that offline.
All right, yeah.
Well, thank you very much.
Thank you. Thank you for attending the talk.